So moving ahead in our journey to building digital circuits, we talked about the transistors, and we took a look at the FET, specifically the field effect transistor, and talked about how that can be used as a switch. Okay, so that's the circuit part. The question now that we are going to explore is we're going to take circuits and then make them do um, logical operations. And then that's where, this concept of logic gates come in. So there are, and without going into the background of gates, if you are interested in understanding how is it that, or who was it who bridged the gap, or not bridged the gap, but who kind of investigated how we can use circuits to implement logic, well, the answer to that is Claude Shannon. So Claude Shannon was the person who, I suppose it was his master's thesis on how to use relays and switches to realize or to implement logic. So he took the Boolean algebra, or I believe the consequence was that we could implement Boolean algebra as circuits. And so the basic circuits, or they are called gates. The basic gates or circuits that we need are the NOT gate, and we'll talk about these: the AND gate and the OR gate. So the idea is this: if you have, so for example, the OR gate, it's represented uh, like so. So two inputs, one output. Right? So let's call this A0, let's call this B0, and then let's call this D0, for example. So we say that this is the OR gate, meaning that this is some sort of a circuit, electrical, mechanical, or what have you, chemical. But in this case, let's stick with the electrical circuits, and somewhere the transistor is useful, and we'll talk about that. So the idea then is that an OR gate, if, and then we have to like talk about the presence or absence of an input. So let's say if A0 as an input is available, B0 as an input is available, D0 will be available. And not only that, so we write it like so, and this is called the truth table. Now, some of you might know it, you might already happen to know this. But if not, the idea is that we have um, different outputs based on the combination of inputs, present or not present. So let's actually, and we can only have like binary states. It's either present or not present. So let's say if, uh, okay, what choice of, okay, let's say we have two values, which is absent or present. So if A0 is absent, B0 is absent, then D0 will be absent. And if A0 is uh, absent but B0 is present, then D0 is present. A0 is present, um, B0 is absent, even then D0 will be present, and if both of these are present, then D0 is present. Now this present and absence, you can give a different name: true, false, 1, 0, um, active, inactive, those kind of names. But the idea is that the behavior of this circuit, the treatment of its inputs, is of this nature. So that's the OR gate. One of the two inputs need to be present for the output to be available. If none of them are available or present, none of them are present, then well, the output is not present. Now the question is, how is that internal circuit implemented? We'll talk about that. The second one is the AND. Now it's represented like so, and then again let's have like A0 and B0 here with the D0. And the idea in case of an AND gate is that both the inputs have to be present for the output to be present. So effectively it translates into something like so, that um, only when both of them, well, both of them are present, um, well, okay, well, both of them are present, that is the only time the output is present. In all other cases, so this is present and this is absent, or this is absent and this is present, or both of them are absent, well, in that case, the output is absent. So this has to be active or available, this has to be active and available, and then this will be active and available only when both the inputs are available. Now, this might sound a bit abstract as to, how can we have something like so and then build circuits out of this? Circuits that can take decision for us, that can follow a sequence. Well, all of that is what we'll learn in this course. But what I wanted to guide in this video was we went from talking about transistor as a switch to transistors implementing gates. And then gates can be combined together to implement complex logic, including memory and state machines. So that is why this concept is important. That is why I'm spending some time on this. Okay, and then the idea of a NOT gate is, well, it only has uh, one input and one output, and it's represented like so, A0 being here and B0, or let's call it D0. So D0. So if A0 is present, the output would be absent, and if the output is present, well, sorry, if the input is absent, then the output is present. So it, so to speak, inverts whatever the input is. And in fact, the other name for this NOT gate is called an inverter. All right, so if you're interested as to how that link between logical reasoning, Boolean algebra or algebra of Boole, how that translated into implementation in the form of circuits, well, do read or do look up Claude Shannon's master thesis and then try to pursue that. That exactly explains how he did the analysis and then used relay circuits, I believe, and switches to implement logical statements, so to speak. Okay, so now let's talk about how the gates are implemented. So let's talk about NOT gate. So we had an input and we had an output, and we said that if the input is available, the sorry, absent. If the input is absent, the output would be present, and if the input is present, the output would be absent. First, we need to now translate input and output into something that's physical, something that understandable. So let's do the following. We'll say that these are essentially voltage signals, right? So these are voltage signals, and for our purposes, we are going to say that these are voltage signals of a certain strength. So either 0 volt or let's say 3 volts. Let's just work with this for now. So presence of a signal would mean that 3 volts is available, and absence would mean that it is 0 volts or voltage is absent. So if I were to draw a circuit like so, um, so let me see. Okay, so if I were to draw a circuit like so, um, actually let me draw a really simple circuit, meaning all parts of it, and let's have like a diode here. This is connected to a battery. Again, in this case, I'm assuming that the current would be limited, that it's not going to be, so to speak, too much. And just to keep the focus on the key idea, that's the intention. So we have the battery here, and this is the plus side, this is the negative side. Okay, and we have the friendly FET here. And so what I'm going to do is I'm going to have a mechanical switch here, and then we'll have like an extra battery here. So let's do it this way, and this battery is 3 volts. So now, and let me also do this. Let me also have something like so. Okay, and there is like a switch in between. So just for imagination's sake, so the idea now is that when we have let's say the gate of the transistor connected to the 3 volts, we would argue that 3 volts is available here. So this is present. And I should have mentioned earlier, but I'm considering the gate to be the input, and the LED lighting up or not lighting up as the output. So this terminal right here, we are treating it as output. And then the question is whether voltage is available or not. So follow this very closely. So if 3 volts is available here, uh, based on the previous lecture or video, this transistor will be a closed switch. It will be active, and so it will be a closed switch. Now all of the current coming from here takes the shortest resistance path and goes down here. Effectively, then there is no or minimal, like very minimal, or in fact no current going this way. And we could argue, like, what is the voltage between these 2 points? Well, if you put a voltmeter here, you will read 0 because, well, it's pretty much a short circuit, has no resistance, no resistance, no IR, no V equals to IR, well, no resistance, so no voltage drop, and so this will read a 0. But interestingly, the same point is connected here, so this voltage will also be uh, 0. And if this voltage is 0, then the LED won't light up. So now what you should notice is that there was an input present, the 3 volts were present, and the output, well, the voltage was absent. Now let's do the other way around, and let me undo many times so that this, okay, thank you for your time. Okay, now what we'll do is we'll say, hey, we are going to turn the switch this way, and now the gate is connected to 0 volts, so the input is absent. But if the input is absent, this is open, and so if this is open, the current will go from here. So the LED lights up. So when you measure the voltage here, well, it should be around whatever the battery's voltage is, or a little bit less. But the idea is that this would be, let's say this is 5 volts. So this would be like 3-ish volts. Idea being that the output is present now. So in this way, if we are to take a MOSFET and say, hey, this is the input and this is the output, and then this is where the power source is, it's called VDD, and then we say this is where the ground is. Well, this circuit behaves like it has all the properties of the NOT gate. So we can then say, hey, active circuit like this, a transistor, active meaning that it consumes power for operation, and all the gates consume, electronic gates at least, not all, but semiconductor based gates, they consume power. They are active circuits. If they are not, do let me know. So, well, that's that. So this was then the NOT gate. And let's talk about the OR gate. So this is also straightforward. What you can say is, let me draw a circuit that will convince you. So we have, um, let's say we have an LED here, and so that is connected to the good old battery. And then what we have here is a transistor, and let's do it this way, and then we have another transistor, and oh, sorry, we have another transistor whose gate is also available here. And what we are going to do is we are going to say, well, uh, okay, let's do this. So we are going to attach our 3 volts battery, and then this point is ground. So this is 3 volts, this is, let's say, 5 volts. I mean, don't try this with 5 volts because the LEDs I know of, at least, they burn. They cannot take more than 3.5 volts in general. Okay, so let's say we have an arrangement like this, and what we are then going to say is that, okay, let's say, So this we are say we're just calling this as our output, and we are calling this as our input 1 or input 0, and this as input 1, right? So now if I were to keep this connection on, then this transistor is on, and so the current will flow from here and the LED lights up. If not that, if I keep this connection active, well, then the current flows from this. And if both of them are active, let's say I have some arrangement like this, well, then the current will flow from both the transistors, and the LED will still light up. The only case in which the LED doesn't light up is, let's say, when both of them are, let's say, tied to meaning connected to ground. If both of them are connected to ground or there is no voltage on them, then there is no path for the current to flow. The current cannot flow, so the LED stays off. And that is in alignment with the truth table of the OR gate. Output is present if either of or both of them, the inputs, are present. It's the output is absent only when both the inputs are absent. So that's the idea. So that's then the OR gate, using again transistor as a switch. And then finally, let's talk about the AND gate. And the way AND gate works is, well, you take two switches or transistors in this case, and then just connect them in series. And you then say that, hey, this is where, the, just a moment. So this is where the output is going to be. Okay, I got a call. That was a spam. Anyways, so the output is available here, and then the input 0 and input 1 is available here, right? So this is one input, this is another one. So, and we say that the output is here, then connect this to the battery. So now if both of these are connected to the 3-volt supply, meaning both the gates are active, only then there is going to be a path for the current to flow and the LED to light up, or the output to be available. If any one of these is inactive, so either this is active and this is not active, then, well, there is no path from here to here. Otherwise, if, let's say, if this is not active and this is active, well, then there is no path from here to here, and hence no path to the LED for the current to flow, that is. And if both of them are, inactive, then, well, there is no path from here to here. So in only that one case where both the inputs are available, will this output be available and the LED will light up. So this effectively then is, well, okay, how do I draw a, yeah, it's a AND gate of this nature. And then up here, well, some okay, this is some, well, this is the OR gate. Never mind, this is what I meant. And out. And so if you put an LED here, let's say, so the LED lights up if any one of the inputs is available. And then what we do not show in the diagrams is that they take in a power supply. It's an active circuit, it needs power supply to operate. Well, that was then the gates. And now there are a few other types of gates which we'll talk as we go along. But the idea is that if you have the NOT gate, AND gate, and OR gate, well, you can pretty much build the rest of the gates. And not only that, there is this particular combination. So this is called the NAND gate. And I'm not going to explain it in detail, but the idea is that there is an inverter or a NOT gate in front of the AND gate. So this combination is called the NAND. And then there is a NOR, and this is called the NOR. And This is essentially the OR gate with inversion in front of it, and this is the NOR. So my claim now is that these two are called universal gates. So just using one of them, you can construct uh, any other gate. You can, for example, if you short these, then this becomes effectively a NOT gate. If you put another gate in front, then this becomes an AND gate, and so on. So, well, that's then the idea. Hopefully, I've managed to convince you that the transistors can be used, the FET in this case, can be used to implement the logical gates, NOT gate, AND gate, NOR gate. And the gates are what we use to then create digital circuits, circuits that obey or that obey logical, let's say Boolean algebra. And given a situation or given some sort of a sequence that you want this electrical circuit to, let's say, generate some impulses or some outputs that you wanted to generate, well, we can use the knowledge of gates to effectively come up with that circuit. We can combine gates together, much like how we combine transistors, and we can come up with digital circuits. And digital circuits then, well, they obey the, or they are based on the Boolean algebra. And the question then is, what can the digital circuits do? So for example, and I'll just leave you with one or two examples, and we'll discuss more in like the next lecture. But let's say if we had uh, two inverters connected like so back to back, and again these are active circuits, so the power is fed to them for operation. This is the input and this is the output, let's say. So now my claim is that this behaves like memory. So let's go from absent and present now to 0 and 1. 1 simply means availability, or the signal is available. Signal in this case is a voltage, voltage at certain strength, and 0 in our case would mean the voltage is absent. So we then say that if the voltage is present, well, at this point the voltage is going to be absent. So this logical value would be 0. And so if this is 0, this will be 1. Now the thing is, if you took the, or well, let's say, if you disconnected the input, then this circuit is now going to feed the 1 back into itself, which will come back as 0, and then the 0 comes here, 1. So this feedback loop, this circuit somehow remembers that the output has to be 0, and that you can then term that this circuit has memory. Why does it have memory? Because it remembers. Even if you took the input away, you did not make the input 0. You did not retain the input to 1. You just let the input be whatever this second inverter is feeding, a second NOT gate is feeding. You just let it be that. And in this case, then it remembers that the initial input you gave it was 1. So this idea of no external input being present, but the circuit remembering a value, well, that relates to memory. That's essentially the concept of memory. And my claim now is the SRAM is implemented using 6 transistors usually. At least that's what I had read. Um, and so they are essentially this feedback loop. Now let's take another case where we wanted to remember 0. So this was the circuit. And what then we'll do is we'll ground this and feed it the 0 volt. So this becomes 1 volt. Now this is 1, so this is 0, and then we disconnect this line. So now all of a sudden, this circuit remembers that the output has to be 1. So in this case, it's remembering that the input was 0 and the output has to be 1. So again, this you can call memory. So what we saw then is just two NOT gates in like back to back connected to each other in a loop. Well, that loop is a feedback, and the feedback essentially results in the circuit remembering what happened to it, what the input was and what the output has to be. And that then is the notion of memory. Anyway, so Not only this, we can implement mathematical operations like addition, subtraction, multiplication, things of those nature. Yeah, and once you have addition, you can increment things, you can decrement things. Once you have that, well, all sort of good stuff can be done. Okay, so that then was the basics of gates and how transistors can be used. FET in our case used to create gates, and these are all voltage controlled devices. And so in the next one, we'll explore the need for FPGA. All right, with this, I'll catch you in the next one.